Hey Honors Physics, Mr. Hausman here. We're going to take a look at Newton's second law in a little more detail today. So over the past day, we've examined the relationship between acceleration, force, and mass. That is to say that Newton's second law says that the sum of the forces are directly proportional to the acceleration, and the mass, being in the denominator, is inversely proportional, meaning bigger forces, bigger accelerations. On the other hand, bigger masses, smaller acceleration. So once you know a little bit about this, you really run into a couple of different circumstances. Is the object accelerating, or is it at equilibrium? Equilibrium means the acceleration is zero. So let's review equilibrium. If the forces add up to zero, we term that an equilibrium. An equilibrium is a state or a condition. By looking at the forces, you can tell if it's at equilibrium or it's not. But there's two kinds. There is a static equilibrium, static meaning it's at rest and the forces are balanced, or it can be a dynamic equilibrium. Dynamic meaning the force is actually doing some constant velocity motion, and it still has balanced forces. This happens often when you're driving at a steady speed on the highway. Little note, equilibrium can happen in one direction and not the other, or you can reverse it and have an x equilibrium, but not in the y direction. So if the object has a lot of forces and they do not add up to zero, then that's actually not an equilibrium, that's an acceleration problem. So really, it really digs down into what are the forces doing. So let's go ahead and analyze a couple, and here's the steps. So we've got a small mouse, a little critter, and it's apparently in free fall. So that means it's experiencing the force of gravity, and that's its only force. So there is no normal force, there's no drag, there's no tension force, so that's the only force. So that object, because the forces have no upward force, this mouse is definitely in acceleration. And we know that that acceleration for free fall is negative 9.8 meters per second squared. Notice the force is downward, so the acceleration is downward, the net force. On the table problem, or this little scenario, let's look for all the contact forces and all the gravity forces. So here's the book. And we're not even going to draw on the table, but we're going to show that it has a weight. Earth is pulling it down, and the table is supporting it. And that's the normal force. And I've drawn those approximately balanced in magnitude, right? Normal looks to be about the same size as gravity. So we have a case where the sum of the forces equals zero, and the velocity is zero. And if those two are met, then we term that a static equilibrium. It's equilibrium because the forces are adding up to 0 newtons, and the velocity is 0 meters per second. On the other hand, it's almost hockey season for our boys and girls hockey team, and this puck is experiencing two forces. Now, interestingly, it mentions there's a velocity to the right, but we never put velocities into our free body diagrams. We only are interested in our forces. So we've got a force of gravity and normal. It's almost the same as the book. In fact, if the puck is already sliding, there are no other forces, right? If it's frictionless ice. So notice the sum of the forces still add up to zero. But this puck, let's put some wind lines in. It's not at rest. Its velocity does not equal 0 meters per second. It's moving faster, right? It's got a velocity to the right. So this would be called equilibrium because the forces add up to zero, but it's dynamic. It's moving as it goes. So really the three conditions you look for are, is it accelerating? Is it in static equilibrium? Or is it in dynamic equilibrium? So let's go ahead and start using this skill. We're going to actually skip the top. You can review that, the big ideas right here. But we have three scenarios. We have here person A and person B, and they're both pushing on the object. And they're both pushing to the right. So one of the first things we're going to need to be able to do is we're going to have to be able to add up forces. These happen to be in the x direction. So we've got positive 40 plus positive 30. So the sum of our forces is 70 newtons to the right. So yes, it has a force that's not 0. Therefore, it has to be accelerating. And in fact, it has to be accelerating to the right. So that would be a case of acceleration and not dynamic equilibrium. Let's go to the next one. We've got person A pushing with 40 newtons, person B pushing with 30, but they're opposite each other. So what we really have is a positive 40 and a negative 30 added, and our net force is 10 newtons. And it's positive, so it means overall this object is pushed, right, has a net force to the right. It accelerates, absolutely, it's not at equilibrium. And the acceleration is whichever direction the net force is. Since 10 represents to the right, then our acceleration is to the right. Finally, what if these two people can't get on the same page? Or maybe it's just some advantage to push at a 90-degree angle to each other. So if we add them, let's take a look at this small free body diagram. We've got a 40 Newton force to the right. We've got a 30 Newton force upward. And almost everyone here knows how to find this resultant. What's the total of the forces? Well, does anyone recognize it as a 3, 4, 5 triangle? So that's a 50 Newton vector. Yes, there's a net force. Yes, there's an acceleration. But the acceleration isn't left or right or up or down. It's at an angle. Now, some of you might be thinking, oh, but it has a little bit of a right component and a little bit of an upward component. But really, the resultant is at an angle. Let's go to the next page. Let's add a little bit of wisdom about the normal force. I know you are familiar with this term. You've done some diagramming of it in our lab on free body diagrams. But let's see all the different ways that the normal force can work. So the normal force is not always equal to the weight. That is the number one misconception that students draw from doing free body diagrams. They deduce that they think they're always the same, and that's not true. It really depends on what other forces are in the situation. So, in fact, sometimes it's not even in the direction of the weight. This person is climbing up, I don't know, maybe it's a stairway, or maybe it's a door frame, and this person is experiencing 4 different normal forces, but yet the force of gravity is downward. So clearly these are not equal and opposite to the weight, but when we add them all up, there is some kind of tension that's going on there that's allowing him to not fall. My nephew used to do this in the doorframe of my brother's house. Not beloved by his brother, or my brother, but he grew out of that. So let's go to a typical scenario. This is definitely typical. This is what everyone thinks of when they think of the normal force. So a normal force is directed perpendicular to a surface, and it's always acting through it, meaning the surface pushes through, the surface is supporting it on an angle here, or it's supporting on an angle there. But the normal force can also change depending on what is around it. So this is an object, and you might say, oh, the normal force is 4. No, let's read the given or the scenario. Every box is at rest, V is 0. We also know that the sum of the forces is 0, or at least we're told that. These are all equilibrium problems. So this must be a pulling force or an applied force. Let's call it a tension. Maybe there's a rope attached. So we have a 4 Newton vector up, that's positive. We have a negative 10 Newton vector down, that's its weight. So the normal force that we would have to draw in here to balance these out would have to be 6 newtons, because isn't 4 plus 6 positive 10, and then negative 10 cancels out. Let's go to the next one. Here, there's a pressure downward on this giant crate. It has a down force of negative 10 newtons, and it has an applied force of another negative 4 newtons. So if this box is sitting on a floor and it doesn't collapse or it doesn't fall, then we know that the normal force must be, instead of 4 or 10, it actually has to be the total of those, but opposite. So we have a positive 14 newtons. And the last one's kind of even weirder. This is a situation where we have an object that is pinned up against the ceiling, And in doing so, someone's pressing it against the ceiling. Well, how much are they pushing with? There's an applied force of positive 15. But the object weighs negative 10. So if you add those up now, we can clearly see that the 15 is bigger than the 10, so the total so far is positive 5. So the ceiling has to push down with a negative 5 Newton force, and then we would be back to equilibrium. And finally, we get to some applications. Let's go take a look at page number, let's see, what page number is this? 16. And let's examine how to use our knowledge of equilibrium and acceleration to solve, in multiple steps, a one-dimensional dynamics problem. So let's take a look and just apply these steps. A fisherman is pulling on a fish. There's a fishing line holding the fish up. So let's draw a free body diagram. So we've got a fish. We've got a fishing line, so that must have a tension in it. And that fish has a weight. It has a force of gravity. It's being pulled down by Earth. And we keep reading the problem and we find out that the force of tension is 50 newtons. It's upward, so it's a positive 50 newtons. And the force of gravity is easily found. This is a 3 kilogram fish, and the formula for the force of gravity is just m times 9.8 meters per second squared. That's negative. So when we multiply 3 kilograms by 9.8, negative, we get 3 times 8 is 24, carrying a 2, 27, 28, 29. We get negative 29.4 newtons. So we immediately have a free body diagram, but now we're also going to quantify it. We're going to be providing quantities for how big these forces are. Then we're going to go ahead and pick a direction. We're going to say that up is positive and down is negative. And we've kind of already included that in our two forces. Third step, let's use Newton's second law. But I'm going to write it the way that we've been using it more recently in class, which shows the direct and inverse proportion. So we don't know the acceleration of the fish, but we do know that there are two forces involved. Tension, and it's in the y direction, and we have to add it to the force of gravity. Then we're going to divide it by the mass. So let's do that over here. The tension is 50 newtons plus negative 29.4 newtons, and we're going to divide that by a mass of 3 kilograms. So 50, let's see, plus if it was negative 30, you'd have 20 left. So I think we would have 20.6. Positive 20.6 newtons. And then we divide that by 3 kilograms. And I'm going to take out my calculator and finish that. And I get, let's change to a new color, and I get an acceleration that's positive of 6.9 meters per second squared. So that fish is pulled quite dramatically with an upward acceleration up out of the water at positive 6.86 rounds to 6.9 meters per second squared. We're going to take a look at other single direction dynamic forces in class over the next few days. Thanks for watching.